Hello and welcome to day 15 of the Jamb Physics in 40 Days series. Now, the Jamb Physics in 40 Days series is brought to you by Oya Learn, where we believe that when you dedicate within 30 to 45 minutes of your time daily, you'll be able to get all the necessary skills and tools that will help you to ace Jamb Physics. So, peradventure, if you're preparing for the Jamb exams and one of the subjects you have selected to write in that exam is physics, then this video is specifically made for you. So please ensure that you check out the videos that we've made from day 1 up until this day 15. Trust me, you do not want to miss any one of those videos, because in each of the videos we have not only looked at the individual topics that are in the Jamb syllabus, but we've also given you tips that will help you to solve questions on those topics with ease, and also we've solved a number of past questions on those individual topics. So it's a video per topic and you really want to check them all out. So check out the video from day 1 to day 15. And also do not forget to share the videos amongst your friends who are also preparing for the exams, so that every one of us can all do well in our exams. So please share the video, like the videos, and also subscribe to the channel. Hit the subscribe button and click the notification bell icon so that you get alerted every time we put out a new content. And also you can practice with the Exam Phone app. The link to download the app is going to put in the description box. So please click the link that will take you to download the app either from the Google Play Store or the Apple Store, depending on your device. The app is designed in such a way that it makes your learning experience fun-like, because it is in a game-like setting where you solve questions at different levels, and then you can then hone your skills and become better at solving many problems in different topics of your choice. So click the link, download the app, register, and trust me, you will not regret that decision. The series is about quantity of heat. Now, what Jamb expects of every candidate preparing for the exam as regards this topic as follows. That is, they expect that every candidate should be able to differentiate between heat capacity and specific heat capacity. Now, many students use this loosely, but you need to know that they are very different from each other. When we are saying heat capacity, you are looking at the amount of heat required to raise the temperature of a substance by 1 Kelvin or by 1 degree Celsius. While on the other hand, specific heat capacity is the amount of heat required to raise a unit mass. Now, mass is measured in kilogram. That is, the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So where one focuses on a unit mass, the other just look at the substance as a whole, right? So when you are considering unit mass, you are looking at specific capacity, but when you do not consider the mass, then you are looking at heat capacity. However, they are related. So for example, in heat capacity, when I say the amount of heat equals the heat capacity, so let's call that Cp, and then theta. Then for specific capacity that considered mass, the heat energy there would then be mass multiplied by specific heat capacity multiplied by change in temperature. So since these two are the same, we can equate them and then say thermal capacity multiplied by change in temperature equals mc theta. So from here, of course, theta cancel theta. So that tells you that heat capacity equals mass multiplied by specific heat capacity. So this is the relationship between heat capacity and specific heat capacity. And you know that the word heat can also be replaced with the word thermal. So when you see thermal capacity, we are still talking about heat capacity. And when you see specific thermal capacity, is still specific heat capacity. So aside from differentiating them like this, you should also be able to determine the heat capacity and specific heat capacity using simple methods. Now, the methods we use is either you're applying the method of mixtures or the electrical method. Now, the simple rule that guides us there is that we apply that provided that no energy is lost, that energy is only transferred from one form to the other. So basically, since it's still heat energy we are working with, we always say that the heat loss by one substance equals the heat gained by another, right? So when you're trying to find the specific heat capacity or the thermal capacity of a particular substance, you can use either the method of mixture or electrical method depending on how the question is set. Like if you are using heating elements, then that is electrical method. But if you are using the calorimeter, then that would be the method of mixtures. Like for example, when you hear a question where a particular hot substance is dropped into a calorimeter containing a liquid, for example, in that case there you see that there is a transfer of heat from a metal to the other by mixing them together. So that would be a method of mixture. And a common one that we do regularly, sometimes even without noticing, is during cold mornings when you mix hot water and cold water so that you can have a lukewarm water that you use to take your bath, right? That is also a way of methods of mixtures. That method can also lead you to help you calculate the specific heat capacity of water or the material, that is the bucket that you're using for the water in that case. So that explains heat capacities and specific capacity by method of mixture or electrical method. And all of this will lead to some numbers of calculations that we'll also be looking at. So you should be able to solve so many numerical problems on the topic as well. Now, for a better understanding on this topic, you can check out our video on this channel where we really discuss quantity of heat in more detail, right? But for now, get your materials and let's solve some past questions on quantity of heat. This question says, a potential difference of 6 volts is used to produce a current of 5 amperes for 200 seconds through a heating coil. Now, the heat produced is, now when you consider a heating coil, it converts electrical energy directly into heat energy. So assuming that no energy is lost in that process, the total amount of electrical energy that is put into the heating coil should produce heat energy. Now, when you consider the options, you see that some options are in calories, kilocalories, while others are in joules. Now, you should know that you can convert from joules to calories. And the relationship is that 1 kilocalorie, that is 1000 calorie, equals 4184 joules. That is the relationship between calories and joules. So let's solve and then we'll pick our answer in the end. Now, we have to convert electrical energy to heat energy. Now, electrical energy is given as the electrical power multiplied by time, right? So that would be IVT equals the quantity of heat. Let's call that H. So to solve for H, that would be the current. Current is 5 amperes multiplied by the potential difference, 6, multiplied by the time. Now the time is 200 seconds. Now before I go on to compute this, it's important that I also mention that electrical energy is not just IVT. It could also be V square over RT. It could also be I square RT. This depends on Ohm's law. You know, Ohm's law says V equals IR. So when you substitute any of these in the equation, you can then change this to this or this. So depending on what you are given. Now I'm using IVT here because I have the current and the potential difference. If I were given, for example, the potential difference and resistance, I would have used this. Or if I were given the current and resistance, I would have used this equation. So please take note of that. Now let's continue. The heat energy therefore becomes, now 5 times 6 would give us 30. Now 30 times 200, that will give us 6,000. And energy is measured in joules. Now if we look at the options, we have 6,000 joules as part of the options. Now if we had not seen 6,000 joules as part of the options, we would have to convert this into calories to see if it matches any of the options we have in calories or kilocalories. So since we already have this, we just go with that option, which is E. In this question from the 1980 UTME, it says, in the study of physics, temperature and heat are often confused. They are often confused with each other. Now, which of the following statements correctly defines these two elements? And truly, when we consider heat and temperature, many students cannot really tell the difference between them. So here's what you can use to always remember the difference between heat energy and temperature. Now, heat energy refers to the total internal energy of a substance as a result of temperature difference. While temperature, on the other hand, is the degree of how hot or how cold that object is. So you see, when one is looking at the total internal energy due to temperature difference, the other one is telling you, okay, this is yay hot, it is yay cold. It's just telling you how hot or how cold something is. However, from the kinetic theory, we can change the definition for temperature as the average kinetic energy of the molecules of a substance. Because now we know every substance consists of tiny particles called molecules that are always in constant random motion. So if they are always in motion, they will have different speed from each other. So the only way to tell their temperature is to find the average kinetic energy of the molecules. So now let's look at the definitions that are here and then see which ones are correct. So option A says temperature is the measure of the average kinetic energy of the molecules of a substance. That is correct. It is just the definition I've given for temperature just now based on the kinetic molecular theory. So option B says heat is the measure of the total kinetic energy of the molecules of a system. And this is also true because when you look at a system consisting of molecules, every of those molecules are in constant random motion, right? So the energy in that system that we now know as heat energy is as a result of their kinetic energy, because those molecules are in motion, so they possess kinetic energy. So that is also true. Now C is saying different materials require different amounts of heat energy to cause a given change in temperature. Now this tells us about thermal capacity. That is, while some substance will just require a little amount of heat for their temperature to change, some will absorb a lot of heat energy and will still not change their temperature. Take for example, there are some things that are called thermal sink in nature, like the sea. Whether you put all the heating elements you can put in the sea, you won't be able to boil the sea because it is a thermal sink. It will continue to absorb the heat energy without having any significant change in its temperature. So that tells you different materials have their threshold, the amount of heat they can take before their temperature changes. You can also do this by comparing between, say, an alcohol-based substance and water, like say ethanol, for example, or methylated spirit and the likes. You see that these things come to a boil very fast. Even with the temperature of your palm, they can begin to turn into vapor, right? Whereas water boils at 100 degrees Celsius. That's because it can take more heat energy than those other materials. So A, B, C seems to be correct. Now D is saying all of the above, while E is saying A and B only. So since we know A, B, C is correct, so definitely all of the above is correct. So we go with option D. In this question, we're told that two liquids P at 20 degrees Celsius and Q at 80 degrees Celsius have specific capacities of, that is, for P, the specific capacity is 1 joules per kilogram per degree Celsius, while the specific capacity for Q is 1.5 joules per kilogram per degree Celsius. And then if equal masses of P and Q are mixed in a lagged calorimeter. Now, when it's a lagged calorimeter, it means we should assume that no heat is lost to the surrounding. Then the equilibrium temperature is, now in this case, we're going to assume that the calorimeter does not absorb the heat as well, that it has a negligible specific heat capacity, that is a negligible thermal capacity rather. So when we apply that, that is the heat lost by the outer liquid, which is liquid Q, will equal the heat gained by liquid P. So let's solve. So let the final temperature, that is equilibrium temperature, be theta, for example. Now heat loss should equal heat gain. So the one losing heat is Q. So let's find heat lost by Q. Now, heat lost by Q would be the mass multiplied by the specific heat capacity of Q, that is 1.5, multiplied by the difference in temperature. Now, it was at 80 degrees Celsius before, so that will be 80 minus the final temperature, that's theta. Now we equate this with the heat gain by liquid P. And remember, it's equal mass, so that will also be M multiplied by the specific capacity of P, that is 1.0, so 1, open bracket. Now the heat gained, that is the final temperature minus the initial temperature, which is 20. Now let's solve this. See, M immediately cancels M. So what we have to do here is open these brackets. Now this can be written as 3 over 2. So 3 over 2 of 80 would be, now 80 divided by 2 is 40. 40 times 3 is going to give us 120 minus 1.5 theta equals theta minus 20. So from here we collect like terms. So we are going to be having 120 minus, no, this becomes plus here, so plus 20 equals, when this goes here, we're going to be having plus also theta plus 1.5 theta. Now, let's take this here now. So what we have here is, when we add these two, we get 2.5 of theta equals, when we add this, we get 140. So we have to divide both sides by 2.5. And then this will give us theta equals, now we can write this as 1400 divided by 25, and then we begin to break it down. 5 goes here 5 times. 5 goes in, now in 140, in 14 that's 2 remainder 4, in 40 that's 8. So we have 28, and then in 0 we have 280. So theta equals 280 divided by 5. Now let's see what this gives us. 5 in 28, that is 5, remainder 3. Now in 30, that is 6. So we have 56. So theta is 56 degrees Celsius. So that is option C. This question says, a good calorimeter should be of, so that is, we are asked about the properties of a good calorimeter. Now, this question is limiting it to specific capacity and heat conductivity of the calorimeter. Now, what a calorimeter is a particular instrument used in the laboratory to determine the specific heat capacity of either an object or a certain liquid. Now, while you are conducting this experiment, you want to ensure that you keep the heat within the calorimeter. That is, the calorimeter should not distribute the heat to the surrounding. That is one thing you want to ensure. Another thing you want to ensure is that the heat that the calorimeter itself is going to absorb, you want to limit it to the smallest amount possible. So that is, the calorimeter should only absorb very little heat from the experiment. So those are the two things we want to ensure in this experiment. Now, how can we define this in terms of specific capacity and conductivity? Now, an object that has high specific capacity is going to require little amount of heat energy it will only absorb very little amount of heat from such an experiment. And then for conductivity, when you don't want the heat to leave that experiment, you have to ensure you are using a material that has low conductivity. So we are saying high specific capacity and low conductivity. So let's look at the options. So option A says low specific capacity and low heat conductivity. That is wrong. We want low heat conductivity but high specific capacity. So we look down and then we see, yes, that is in option C, where we have high specific capacity and low heat conductivity. So the answer is option C. This question was set in 1986 and then repeated in 2017. So it's a common question, and questions are usually set in this direction too sometimes. So just take note of that. Now, but the question says, when two objects P and Q are supplied with the same quantity of heat, the temperature change in P is observed to be twice that of Q. Now, the mass of P is half that of Q. So the ratio of the specific capacity of P to Q is, so we have to find the ratio of their specific heat capacities. Now, let's start with the information we have. We know their quantity of heat is the same, therefore M of P, C of P, and theta of P should give you M of Q, C of Q, and then theta of Q. Now, we know that M of P is 1 over 2 M of Q. Okay? Now, what this implies is that 2 MP equals MQ. Now, we also see that the temperature change in P is observed to be twice that of Q. So, theta P is going to be twice of theta Q. Now, noting that, that's basically all the information we have here. So let's go on to then find the ratio of their specific heat capacities. So from here, I can say C of P divided by C of Q is supposed to be M of Q theta Q divided by M of P theta P. Now, working with this, we see their relationship. From here, we already see that M of Q is twice M of P. So 2MP. And then theta Q. Oh, theta P is twice of theta Q. So I'm just going to put theta Q here over. Now M of P is half of M of Q. So since we already have M of P here, I'll keep this as M of P so that it can cancel out. And then here we see that theta P is twice of theta Q. So I put this as 2 theta Q. So let's see what we have. Cp over Cq is therefore, now the 2 here cancels 2. So M of P here 1, M of P here 1, M of Q here 1, M of Q here, theta Q rather, 1. So what we have is 1 over 1. So basically the ratio of their specific capacity is 1:1. And that is option C. 22,000 joules of heat is required to raise the temperature of 1.5 kilograms of paraffin from 20 degrees Celsius to 30 degrees Celsius. Calculate the specific capacity of paraffin. To find more questions like this that will help you improve on your skills, do download the Exam Fund app. The link to download the app is added in the description box, which will lead you to download either from the Google Play Store or the Apple Store depending on the device you use. Please download and register and play. It's like a game format where you solve questions at different levels on your subject of choice. So definitely you get better at solving problems and it is done in a very fun way. And also don't forget to subscribe to the channel. Please click the subscription button and the notification bell icon so that you get alerted every time we put out a new content for you. Now, to solve this question, we have the quantity of heat supplied already, and we have the mass of paraffin oil, and we also have the temperature change, which is from 20 to 30. That gives us 10 degrees. So now let's find the specific heat capacity. So we know that the quantity of heat is given as mc theta. So to find specific capacity C, that will be the quantity of heat divided by mass multiplied by temperature change. Now, the quantity of heat is 22,000 joules divided by the mass, which is 1.5 kilogram, multiplied by the temperature change. The difference here is 10 degrees Celsius. So C therefore is, now when we multiply this, we're going to be having here 22,000 joules divided by, this will give us 15 kilogram degrees Celsius. And when you divide this, you're going to have 1,466.66 joules per kilogram per degrees Celsius. Now, when we consider the options here, the closest option is option A. So we go with A. Now, this question says the amount of heat needed to raise the temperature of 10 kilograms of copper by 1 Kelvin is 8. Now, the trick to this question is that mass is mentioned. Now, here is how you tell whether we are talking about specific capacity or just thermal capacity. Now, in the definition for specific heat capacity, it is said that it is the amount of heat required to raise the temperature of a unit mass. So that is, it has to be 1 kilograms specifically. Now, if you are not looking at 1 kilogram of a substance in your definition, then it is just thermal capacity. So since this question is looking at a substance which is 10 kilograms, then it won't be specific capacity, but rather just the thermal capacity or heat capacity. So in this question, the answer is option B. How long does it take a 750 watt heater to raise the temperature of a 1 kilogram of water from 20 degrees Celsius to 50 degrees Celsius? Now, this is something you can also try at home when you have a heater. It may not be exactly the same because you have to factor for the fact that some of the heat will be lost to the surrounding. But using this method, you too can determine how long of a time it will take to bring your water to a boil or to take it to a certain desired temperature. So let's see how it is done. So in this case, the electrical energy is going to be converted into heat energy, and we're going to assume that no heat is lost to the surrounding. So the electrical energy would be the power multiplied by time. So the power is given as 750. So we say 750 watt multiplied by the time. Now that is what we are asked to find. So let's call that T equals. Now when we convert this into heat energy, considering the specific capacity of water, we're going to apply the mass of water, which is 1, multiplied by the specific capacity, which is 4,200, multiplied by the temperature change. So we are taking it from 20 degrees to 50 degrees, and the difference there is 30. Now, to get time, T therefore would be, now we're going to use 1 times 4,200 remains 4,200. Then we multiply that by 30. And then we divide it by 750. Now, when you compute this, you should get 168. And time is measured in seconds. So the correct option here is C. This 1992 UTME question asks how much heat is absorbed when a block of copper of mass 0.05 kilogram and specific heat capacity 390 joules per kilogram per Kelvin is heated from 20 degrees Celsius to 70 degrees Celsius. Now here's the solution. Now the quantity of heat equals mc theta. Now the mass is 0.005 kilogram, which is basically 5/100 in kilograms, multiplied by the specific capacity, which is 390, and then multiply this by the temperature change, which is from 20 to 70. That will give us 50 here. So we can then break this down. 0 cancel 0, 0 cancel 0. So we have 5 times 5 times 39. That is 25 times 39. And this should give us 975 joules. So now that we have this, when we look at the options here, they are in standard form. So this can then be written as 9.75 times 10. So since we move 2 places, that will be 10 raised to power 2 joules. So the correct option is therefore B. When 100 grams of liquid L1 at 78 degrees Celsius was mixed with X grams of liquid L2 at 50 degrees Celsius, the final temperature was 66 degrees Celsius. Now, given that the specific capacity of L2 is half that of L1, find X. To solve this question, we're going to equate the heat loss to heat gained. And in this case, since liquid L1 is the hotter one, liquid L1 will be losing heat, while liquid L2 will gain heat. That is mL1 multiplied by CL1 multiplied by change in temperature in L1 equals mass of L2, specific capacity of L2, and then change in temperature in L2. Now, we know that the specific capacity of L2 is half that of L1. So if CL2 equals half CL1, what this implies is that CL1 equals 2CL2. Now, let's apply the rest of the information to solve this question. Now, mass of L1 is 100 grams. So 100 multiplied by CL1, so let's just call that C, multiplied by, then put the L1 so that we don't have confusion. Now, change in temperature for L1. L1 is moving from 78 degrees to 66. Now, the difference here is 12. Now, we equate that with, now, mass of L2, that is X, multiplied by the specific capacity of L2. CL2 is half of this, so CL1, and then we multiply this by the change in temperature in this case from 50 to 66. That will give us 16. So 16. So we can say 2 year 1, 2 year 8. Now, to get X, because CL1 here will cancel CL1 as well. So the value of X would then be, now 100 times 12 here is 1200. Now we have to divide this by 8. So let's see what we're going to get now. So X is 1200 divided by 8. So X therefore becomes, now 8 here 1, 8 in 12, that will go once with a remainder of 4. Now 8 in 40 is 5, and 8 in 0, that's 0. And since we're working in grams, that will be 150 grams. So the correct option is C. This question says an electric kettle of negligible heat capacity is rated at 2000 watts. Now, if 2 kilograms of water is put in it, how long will it take the temperature of the water to rise from 20 degrees Celsius to 100 degrees Celsius? So the temperature change here is 80, the mass is 2, and the specific capacity of water is given as 4,200 joules per kilogram per Kelvin. Now, in this case, we're going to equate electric energy to the heat gained by the water. So here's the solution. Now, the electrical energy is power times time. So the power is given as 2000 watts multiplied by time T. Now, this equals, now the heat gained by the water would be the mass of water, which is 2, times specific capacity 4200 multiplied by the temperature difference. So the temperature changes from 20 to 100, that will give us 80. Now here we can make T the subject, and then we have 2 times 4200 times 80 all divided by 2000. Now 0 cancels 0, 0 cancels 0, 0 cancels 0, 2 here 1, and then 2 here is gone. So what we have is 42 times 8. Now T then becomes, now what is 42 times 8? 8 times 2 is 16, so 6 carry 1, 8 times 4 is 32. 32 plus 1, that's 33. So we have 336 seconds, and that is option B. If you are still not subscribed to the channel, I'd like to implore you to please do so. Please hit the subscribe button because when you subscribe, you're helping us to be able to make more helpful content like this. So please hit the subscribe button and also click the notification bell icon so that you get alerted every time we put out a new content for you. And also don't forget to like and share the video amongst your friends to help them also perform well in their physics exams. So please like and share. And if there's any question at all you would like us to attend to, perhaps during your study you came across a question and you would like our help to help break it down or solve it for you, please drop it in the comment section. We'll definitely attend to it. And you can also drop any comments you have. If there's anything you'd like us to attend to, please put it in the comment section. I promise we'll attend to your own comment as well. In this question, we're told that a 500 watt heater is used to heat 0.6 kilograms of water from 25 degrees Celsius to 100 degrees Celsius in T1 seconds. Now, if another 1000 watt heater is used to heat 0.2 kilograms of water from 10 degrees Celsius to 100 degrees Celsius in T2 seconds, we have to find T1 divided by T2. Now, we have to consider that the water in this case have the same specific heat capacity C. So to solve this, here's what we do. Now, in the first case, the electric energy consumed is going to be power times time, which is 500, multiplied by the time, which is T1. And then we equate this to the mass of the water, which is 0.6, multiplied by the specific capacity C, multiplied by the temperature change. From 25 to 100 will give us 75, right? So T1 in this case therefore becomes 0.6 times 75 times C divided by 500. Now this would give us 0.09 C. Now for the second case, we have the energy as 1000 watts multiplied by the time, which is T2, and this would be the mass, which is 0.2, multiplied by the same specific capacity C, multiplied by the temperature change, which is from 10 degrees to 100 degrees. That would give us 90. Now, to get T2 here, we say T2 here equals 0.2 times 90 times C, all divided by 1000. So what that means is that T2 is going to give us 0.018 C. Now we can go on to find T1 over T2. Now that will be, remember T1 is 0.09 C divided by T2, which is 0.018 C. So C cancels C. So we can then solve this with our calculator. That is T1 over T2 is going to give us 5. So the option to go for here is B. To solve this 1999 UTME question, let's look at what we have from the facts from the question. Now, we see that a piece of substance of specific capacity 450 joules per kilogram per Kelvin falls through a vertical height of 20 meters. So specific capacity is 450. The height is 20. And we are given G as 10 meters per second squared. Now, we are to calculate the rise in temperature. And that's about it. So looking at what we have here, we know that according to the question, all the energies are converted into heat. And when an item is falling, in this direction, this is where it's going to have its maximum potential energy, and this is where it's going to have its maximum kinetic energy. And at this point, the potential energy equals kinetic energy, because here kinetic energy here is 0, and here potential energy equals 0. So that is, at this point, the kinetic energy here is the same as the potential energy at the top here. So we can easily equate the potential energy to the heat gained by the material. Now, potential energy here is mgh, while the heat gained is going to be mc theta, where theta is the temperature change. Now we equate both sides, so mgh equals mc theta, so m cancels m, and then we can go with the rest. So that is gh equals c theta. Now g is 10 multiplied by h, which is, according to the question, 20. H is 20. Now we equate this to c, where we have 450 here, times theta. So the change in temperature therefore becomes 10 times 20. That will give us 200 divided by 450. So let's break this down. 0 cancels 0. Theta therefore becomes, now what can go? 5 will go. 5 will go here 4 times. 5 will go here 9 times. So we have 4/9 degrees Celsius. So the option we go for is therefore B. A metal of mass 0.5 kilograms is heated to 100 degrees Celsius and then transferred to a well-lagged calorimeter of heat capacity 80 joules per Kelvin containing water of heat capacity 420 joules per Kelvin at 15 degrees. So we know that both the calorimeter and the water are at 15 degrees and their specific thermal capacity has been given. So if the final steady temperature is 25 degrees Celsius, find the specific capacity of the metal. Now we know that the metal is going to lose heat to the calorimeter and the water. So how do we solve for specific capacity of the metal here? So heat loss by the metal is the mass of the metal, which is 0.5. Let's write that as 1/2 kilograms multiplied by the specific capacity multiplied by the change in temperature. That is 100 minus final steady temperature is 25. So what we're going to be having here is 1/2 times 75 times C. That's the heat loss. Now, heat gain by calorimeter. Now, that's going to be the thermal capacity times change in temperature. Now, the thermal capacity of the calorimeter is 80 multiplied by the temperature change, which is from 15 to 25, so 25 minus 15. Now, what we have here is 80 multiplied by 10, and that will give us 800. Now, heat gained by water. Now, that's going to be the thermal capacity of water, which is 420, multiplied by the temperature difference, so 25 minus 15. And this would give us 420 times 10, that is 4,200. Now, heat loss equals heat gain. So therefore, we'll be having 72C/2 equals 800 plus 4,200. So this is 75, I mean. So 75C/2 equals, when we add this, we're going to have 5,000. which implies that 75C equals 2 times 5,000, that's 10,000. So the specific capacity C will be 10,000 divided by 75, and that will give us 133.33, and specific capacity is in joules per kilogram per Kelvin. So the correct option here is option C. A block of aluminium is heated electrically by a heater rated 25 watts. If the temperature rises by 10 degrees in 5 minutes, the heat capacity of aluminium is... Now, the electrical energy used to heat up this aluminium can then be given as 25, which is the power, times the time, which is 5 minutes. Converted to seconds will be 5 times 60. Now, we equate this with the thermal capacity, let's call that Cp, of aluminium, then multiplied by the temperature change, which is 10. So from here, we can then say the thermal capacity is 25 times 5 times 60 divided by 10. So 0 cancels 0, and then the thermal capacity of aluminium will be 25 times 5 times 6, and that will give you 750, and it's in joules per Kelvin. So the correct option is B. Now, to practice more, you can try out the Exam Fund app. The link to download is in the description box of this video. You can download from Google Play Store or the Apple Store depending on your device, and then you get to practice many more questions in any subject of your choice. And also don't forget to like and share the video, and also subscribe to the channel by clicking the subscription button, and also click the notification bell icon so that you get alerted when the next content is put out. Thank you for following this series. I'll see you in the next video.